Hello, welcome back. You may recall in our previous video, an example, we looked at finding the area bounded between two curves using a double integral. Now, it's a lot of writing, but you'll kind of get the hang of it where you just pretty much look at the graph and write your integral. And that's where we want to get. And you'll find out this is actually something easier than in single variable. But notice, my function here was in terms of x. And we said if it's in terms of x, we're going to use the order dy dx. Because my vertical is going to give me my change in y's, which will be in terms of x. But what if we want to switch it? What if instead of using dy dx, we want to do dx dy? So let's talk about that. In example 3, we start with the vertical. Now the vertical is always our change, gives me my change in y. This will help avoid having issues to use inverses. Recall last year in single variable, we had to use inverses to calculate the area or volume. For example, if my function was in terms of x, if my function is in terms of x, but my rectangle is perpendicular to the y-axis, we had to switch variables. So let's try to do that with multiple variables. And you're going to find out this is not so user-friendly. So this time we're going to start using with a horizontal rectangle, or we're going to start with delta x. So my area now is going to be instead dy dx, but dx dy. So now, because of this, we have to be, oops, I don't know what happened there. Because of this, we have to be in terms of y. So we have to write our equation now in terms of y. So let's take a look here. First of all, let's just deal with our rectangles. So because I'm doing my x first, I'm starting with the horizontal rectangle. And here's what the problem is. Part of the problem. If I start with my horizontal rectangle, my change in x doesn't look so bad. It's going to be, but remember, we have to be in terms of y. So my horizontal rectangle is going to start at 0, but where does it end at? Where does this end? Well, this end right here is my function right here. That was my sine curve, but that was sine of x. So we have to rewrite this, and we know that if we have y equals sine of x, I could write x as inverse sine of y. So that's what this end piece right here would be the inverse sine of y. But it even gets even crazier, okay? Because what happens once I meet this intersection point right here? What happens once we get to that point, pi over 4, root 2 over 2? Well, my right side changes. So I have another one I have to deal with. So my change in x, so my next change in x would be starting at 0 again. But where would this end up at? Well, that is my inverse cosine. So we know that y is equal to the cosine of x, so therefore x would be the inverse cosine of y. So we're going to have two integrals here. And of course, because this is where it splits. So now we have to deal with our vertical rectangle. So let's go ahead and get our verticals. So for the first one, changing y, my first one starts right here. There's my first one. Now the smallest y value is going to be 0. And the largest y value is going to be the root 2 over 2. For the second change in x, we start up here. The smallest y value is the square root of 2 over 2. And the largest it will ever be is 1. And from here, now I can write my area, but I have to use two integrals. My first one, dx dy, be careful because we're in terms of y now, we start with dx. And my change in x's goes from 0 to the inverse sine of y, and then from 0 to root 2 over 2. There's a quick way you can tell if you did this setup correct. When you set up your first integral, this dx part right here, your domain should be in terms of the outside variable. So I'm going to add another one, dx dy. It doesn't make a difference if you split it. Go back the other way around. So this is going to go from 0 to the inverse cosine of y. Again, check it. Does my y match up my outside variable? And the outside, root 2 over 2 to 1, should be numerical. And this would give you the same exact area, although not as easy to solve. Anyways, so simply put, if the function's in terms of x, just use dy dx. If the function's in terms of y, you can switch it. But if the function's in terms of x and you want to make it y first or dx first, you have to use your inverses. Hopefully that's not terribly confusing. So let's do some examples down here. Ready? We want to write two double integrals that will find the area of the shaded region. So let's take a look at part A right here. Alright, so for the first one, I'm going to use dy dx. Now if I use dy dx, remember this is telling me that my vertical must go first. In other words, we're looking at the change in y values. So I can get my change in y values. So if I draw my vertical rectangle, there it is. Ready? What's my smallest y value? Going to be 0. And what is the largest y value going to be? So what's my largest y value? Well, my largest y value is going to be that 2x. So remember, we want to be in terms of x. Now, another way to get the horizontal part is if you don't have to do the horizontal part, all you really got to do is kind of think, well, this rectangle is now going to slide. The x value is going to slide from 0 all the way to 1. 0 to 1. I'm going to slide that vertical rectangle from 0 to 1. So my x values are going to go from 0 to 1 right there. So I can write my integral now. My area would be the double integral dy dx. The y's go from 0 to 2x and the x's go from 0 to 1. That's one way I could write it. Now the other way we could do it is using, I'll use a different color this time, purple. I'll use dx dy. But be careful, we have to be in terms of y now. So we have to do some algebra here, okay? Let's do some algebra. Ready? If y equals 2x, and I could say x equals 1/2 y. So this is going to start us off with the horizontal rectangle. So we start off with horizontal. So let's see here. So that's going to be my change in x's. Well, if I look at the horizontal rectangle, ready? What's the smallest it's going to be? Well, the smallest my horizontal rectangle is going to be is that line x equals 1/2 y. The largest x will ever be is 1. And then I'm going to slide it. Ready? I'm going to slide that horizontal rectangle from 0 all the way up to 2. So remember, this is going to slide up and down on the y-axis from 0 to 2. And I can write my area now, double integral dx dy, and that's going to go from 1/2 y to 1 and from 0 to 2. And you have your area, you can't even see it, and you have your area function right there. Sorry about that. Alright. Now, so let's take a look at another example here. What if we deal with like a circlet or a parabola in this case right here? Alright, so I know I'm going to be doing it twice, so I might as well go ahead and solve. If x equals y, I can say that if y equals x squared, I can say x equals plus or minus the square root of y. So let's go ahead and set this up. Let's do our vertical first again. So we can go ahead and do dy dx first. So this says, remember this has to be in terms of x. So let's draw a vertical rectangle. There it is. So my change in y's, well, what is the smallest y value is going to be? That's going to be our parabola itself, x squared. What's the largest my area is going to be? Just 1. Ready? The change in x, well, what's the smallest x value is going to be? -1 all the way to +1. So my area, dy dx, so you change in y's first, x squared to 1, negative 1 to 1. And that would find me my area right there. Again, what if we want to do dx, dy? Well, now we have to be in terms of y. Be very careful with this one. My change in x first, okay? So if I do horizontal, ready? What's my smallest? Remember, this is now in terms of y. And what's my largest y value? Now you can use symmetry on this one if you wanted to. So my smallest y value is going to be the negative square root of y. And the largest will be the positive root y. So we would go from negative root y to positive root y. And then the y values, we're going to slide this up and down now. The smallest y value for that rectangle will be 0. And the largest will be 1. So my area, dx, dy, we would go from negative root y to positive root y from 0 to 1. And that also would find our area right there. As you can tell, these aren't too bad to do. You can, like I said, you should be able to set these up in your head. All right, let's take a look at one last example, then we'll go to another video. We'll take a look at how we can, given the domain, draw the original graph. All right, so let's take a look here. So again, we want to write this twice. So the first one we're going to use, of course, is dy dx. Remember, for this one right here, we want to put this in terms of x. So when I look at my vertical rectangle, here, my vertical rectangle, what is the smallest my vertical rectangle is going to be? And that's the square root of x. The largest, that's just 1. So I know my change in y's, dy, my change in y is going to go from the square root of x all the way to 1. My change in x's, well, this is now going to go right and left, right? Starting at 0 and going to 1. I can write my area, root x to 1, 0 to 1. You get really fast at that. Dy dx. And there's your area. And the next one, what if we want to do dx dy? Remember, in this case, we are in terms of y. So let's take a look. So now we're going to go horizontal. Ready? What's my smallest? Well, that's just 0. My largest, oh no, be very careful. My largest, be careful right here, okay? We got y equals square root of x, so therefore we can say x equals y squared. So my largest here is going to be y squared. So my domain, my change in x's, is going to go from, I guess I should just say delta x, goes from 0 to y squared. And then my change in y, well, that's just going to, this little rectangle, remember, is just going to go up and down from 0 to 1. So that's going to go from 0 to 1, and then my area would be 0 to 1, 0 to y squared, dx dy, and both are acceptable for us. All right, go on to the next video. Hope you enjoyed this. Go on to the next video, and we will take a look at just how we can, given the domains, go into the graph. We'll talk about that next. Bye-bye.